What's up, everyone? We're here in section 7.5 looking at utilizing double and half angle formulas to evaluate trig functions. So let's start with the double angle formulas first. I have formulas for sine, cosine, and tangent all on your screen. And of course, they can be utilized with reciprocal identities to also evaluate for secant, cosecant, and cotangent as well. All right. Now, the name double angle formula can be somewhat misleading, okay? The reason these are called double angle formulas is because the angle that you're trying to evaluate for is being thought of as double some smaller angle, all right? So let's say for any one of these formulas, we're actually trying to evaluate for the angle theta. Well, theta is being thought of as 2 alpha, okay? So you're thinking of your angle as double some smaller value alpha, all right? That's misleading though, in that really to utilize the formula, you need to take your original angle theta and cut it in half in order to know what alpha should be to utilize the formula, okay? So again, they're called double angle formulas, but you essentially will be needing to divide your angle in half in order to utilize these formulas, all right? The other thing to draw your attention to is for cosine, there are 3 double angle formulas, okay? Those are all listed in blue there, and which one you use is solely on preference, okay? So I have several examples related to these formulas. Let's start with the one over on the left here to find sine of 120 degrees using a double angle formula. Now, I really don't need a double angle formula for this particular function. However, just want to show you how it can be utilized still, right? So your angle is 120 degrees. Let's call that alpha, or I'm sorry, theta, all right? And then what you're going to need to do is divide that by 2, okay? And that'll tell you what alpha should be, all right? So alpha is going to be 60 degrees. So we're now going to think of sine of 120 degrees as the sine of 2 times 60 degrees, okay? Then we can apply the formula that's at the top of the screen in red. Sine of 2 times 60 degrees is equivalent to 2 times sine of 60 degrees times cosine of 60 degrees, all right? And then you're going to evaluate both sine and cosine of 60 degrees. All right, now sine of 60 degrees is radical 3 over 2. Cosine of 60 degrees is 1/2. All right, so we're going to wind up with 2 radical 3 over 4, which simplifies to radical 3 over 2. Okay. All right, second example. Simplify cosine squared of 5 theta minus sine squared of 5 theta. All right. And what I want to recognize is that that expression follows this format right here. Okay. Which means I can apply a double angle formula for cosine. I can think of 5 theta here as alpha for this particular formula, okay? So that means this is equivalent to cosine of 2 times 5 theta, or cosine of simply 10 theta. All right, so that's all we're wanting to recognize there. All right, last example. If sine of theta is equal to 4/5, and theta is between pi over 2 and pi, meaning it's in quadrant 2, find sine of 2 theta, okay? So let's draw out that angle theta. right, to where y is 4, r is 5. That's going to make x -3, okay? And I'm going to apply my double angle formula for sine. Sine of 2 theta is equivalent to 2 times the sine of theta times the cosine of theta. Now I already know the sine of theta to be 4/5. But the cosine of theta, I was not directly told. That's why I drew the picture out. With the picture, I can tell you that cosine is equal to -3/5 here. Okay, so now multiply that all out, and you'll end up with -24/25 for the value of sine of 2 theta. Okay, all right, moving into the half angle formulas. All right, the reason these are called half angle formulas is because you're thinking of your original angle as some larger angle cut in half, okay? Which really means in order to utilize these formulas, you really have to double your original angle, okay? Now, notice that for all three half angle formulas, sine, cosine, and tangent, you have a square root built into the formula with plus or minus in front of it, okay? And this is crucial. The plus or minus, whether you choose the positive square root or the negative square root, is dependent upon which quadrant theta over 2, which is the original angle, which one that's in, okay? So make sure you keep that in mind, all right? The other thing to notice also is that tangent has 3 double angle formulas. If I'm being honest, I would probably be hesitant on using the one that has the radical, just because the simplifying can get nastier on it than utilizing the other 2 formulas. Okay, so let's use a half angle formula to find sine of 195 degrees. Okay, so I'm evaluating for 195. When it says use a half angle formula, that tells me I should actually be doubling the angle I'm evaluating for, which takes me to 390 degrees. And notice 390 is very useful because it has a nice 30-degree reference angle associated with it, okay? So I'm going to think of sine of 195 degrees now as equivalent to the sine of this larger angle 390 divided by 2. So that's again why this is called a half angle formula, okay? All right, now apply your sine half angle formula, which is in red here, okay? And it's going to start off with the square root of 1 minus the cosine of that 390-degree angle all over 2. And then we also have to determine, should we keep this a positive square root or a negative square root, okay? And that's dependent upon the original angle of 195 degrees. That's in the third quadrant, right? In quadrant 3, sine is negative, right? So that tells me I need a minus in front of my radical here, okay? All right. So now we just have to evaluate for cosine of 390 and then simplify as much as we can, okay? So let's draw out 390. So that's again going to take you to a reference triangle of 30 degrees in the first quadrant. Okay. So cosine there is positive radical 3 over 2. So this is going to become the negative square root of 1 minus positive radical 3 over 2, all over 2. And now from here, it's how good your algebra and your ability to simplify, okay? I would suggest there's a couple different ways to simplify here, but I would focus on what's underneath the radical right now and simplifying that by simply combining the 1 minus the square root of 3 over 2 into a single fraction. So that's going to become negative square root 2 minus the square root of 2 over 2 all over 2. Okay. And then I'm going to multiply by 2 over 2 here. That'll get these to wipe out, and I would be left with the negative square root of 2 minus the square root of 3 over 4. And then notice that radical applies to both the numerator and the denominator of that fraction, which means I can break this up and I can think of it as the negative square root of 2 minus the square root of 3 over the square root of 4, which is really just 2. So it rationalizes itself, okay? And we're not really used to having expressions where we have a radical within a radical, but that's acceptable in this case. We'll say this is as simplified as we can get, okay? All right, one final problem. Here's an identity to establish. We want to show that cosecant of 2 theta is equal to 1/2 times the secant of theta times cosecant of theta. All right. Now you might argue that the right side of this identity is more complex than the left side, but I disagree. I think cosecant of 2 theta is more complex because of the fact that the argument there is 2 theta rather than just theta. So that's where I'm going to begin. I'm going to take cosecant of 2 theta, and first thing I'll do is apply a reciprocal identity and think of this as 1 over the sine of 2 theta. And then I can apply a double angle formula for sine of 2 theta. That's equivalent to 2 times the sine of theta times the cosine of theta. And I'm going to break this up. It's the same as 1/2 times 1 over the sine of theta times 1 over cosine of theta. And of course, we know that 1 over sine of theta is cosecant of theta, and 1 over cosine of theta is secant of theta, which is essentially what we're trying to prove, but let me reorder it. They wanted secant of theta first. And we're verified.